Jump past question 2001. Question number 45. At resonance, the phase angle in an AC circuit X. Our question is centered on resonance of an AC circuit. Resonance. In AC circuits, we have common components like resistor, capacitor, and inductor. Okay, these are the circuit symbols. These are common components in our AC circuits. And these components determine whether our circuit is resonance circuit or not. Okay, observe. These components come with resistance. The resistance of a resistor is resistance. Resistance of a capacitor is capacitive reactance. Resistance of an inductor is inductive reactance. If you have a circuit or a circuit diagram and you have a capacitor in it, then we'll say that the current and the voltage, the AC current and the AC voltage in that circuit will be out of phase. Please make attention. Let me start with a resistor. If I have a circuit diagram, AC circuit diagram that contains only a resistor, I can say that the AC current and the AC voltage are in phase. If I have a resistor, only resistor, the voltage and the current, AC voltage and current, are said to be in phase. What does that mean? They move in the same pattern. None is ahead of the other and none is lagging behind. They move together. That's what I mean by phase. At every point, they maintain the same angle. None is faster, none is lagging behind. That is phase angle difference of 0. That's when we have only a resistor. Are we together? Then let's now involve a capacitor in our AC circuit diagram. Something will happen. Then the current and the voltage will now be out of phase. One becomes faster than the other. And the question is, which one is faster, which one is lagging behind? Pay attention. For a capacitor, the current begins to lead and the voltage begins to lag. Then there is phase angle difference of 90 degrees. If you have a capacitor, then current leads, voltage lags. Voltage lags behind. Then this happens at phase angle difference of 90 degrees or radians over 2. Radians is synonymous to 180 degrees. So rad over 2 is the same thing as 90 degrees. This is not pi, this is rad here. Rad is 180 in the radian world. Then rad over 2 is the same as 90 degrees. So if you have a capacitor in your AC circuit diagram, the current will lead the voltage. That's what a capacitor does to our AC circuit. It favors current more than voltage. Then the current and the voltage now are now out of phase. Then coming to an inductor. Inductor also behave similar to capacitor. Inductor will make the current, the AC current and the AC voltage to be out of phase. Out of phase. Then the question is, if they are out of phase, which one is faster, which one is what? Slower. Then let's what happens here. The opposite happens here. Here the voltage leads and the current lags. Are we together? Then lagging is in current under inductive AC circuits. Then the phase angle difference is the same. It will also be 90 degrees or rad over 2. Rad over 2. So what point am I making now? Purely resistive circuits is resonance. Phase angle difference of AC circuits, phase angle difference of AC current and voltage is 0. Then purely capacitive is out of phase. Purely inductive circuit is out of phase. Then we can also have an inductor. We can also have an inductor and a capacitor and a resistor in a circuit, and the circuit will still be at resonance. So the question becomes, what happened? So in that circuit, we'll find a way to make the capacitor and the inductor to cancel. Are we together? I can have a circuit diagram that contains a resistor, a capacitor, and an inductor, and at the end it will still be a resonance circuit. And what happened there? What happened there is that I manipulated the inductive reactance and the capacitive reactance to cancel. I'll find a way to make the resistance of the inductor and the capacitor to do what? To cancel themselves and go back to zero. Then if you don't clearly understand the logic, I'll give you mathematical approach to still get your answer. There is a way we solve for angle of resonance in AC circuits. Okay, what determines this resonance circuit is the resistance, or what we call impedance. Another name for resistance, total resistance offered to the flow of currents in a circuit. When we have more circuit components, we use the term impedance. Okay, then the formula says to get the resonance angle, we say cos theta is equal to resistance over impedance. Resistance over impedance. Then I made mention of something earlier. A circuit diagram that contains resistor, inductor, capacitor can also be at resonance. How? I have to manipulate the inductive reactance to cancel the capacitive reactance, and the only way is to make them equal. Then to get the impedance, impedance is given as square root of R squared plus open up brackets, inductive reactance, the resistance of an inductor, minus capacitive reactance, all squared. This is my impedance. Okay, observe. The only way this can become a resonance circuit is that these two things become equal. SL becomes equal to XC. That's the condition that a circuit that contains inductor and capacitor will also be resonance circuit. Then let's see what will happen. Then Z now is equal to square root of R squared. Since they are now equal, the same number being equal, it will give us 0. 0 squared will also be what? 0. Then this reduces to this. So this is now what we have in that circuit. Then square cancels square roots. Z becomes equal to resistance. So you can see that thing is the same thing as purely resistive circuits. When they match, the circuit returns to containing only a resistor. It now becomes purely resistive circuit again, where we have the AC currents and the AC volts in phase. In phase means the same angle. When the same angle minus, you get 0. 90 minus 90, 0. That's why at resonance, the phase angle difference is what? 0. Let's still prove it. Then coming back here, then cos theta. Forgive me, you cos an angle. My apologies. You cos an angle, cos theta is equal to resistance over Z. Then notice they are the same. These are equal. This one we proved here. Since these two are equal, at the end we also have these two equal. So when equal things cancel, we get 1. Therefore, let's get the theta, the phase angle difference. Then cos the other one becomes cos inverse. Cos inverse of 1. When you do cos inverse of 1, you'll be getting 0 degree. So mathematically, we've also proven that a purely resistive circuit is in phase. Phase angle difference 0. Purely inductive and capacitive circuits are out of phase. Phase angle difference 90 degrees or rad over 2. Thank you. Please stay tuned and do subscribe.